This video is on applying Newton's second law of motion to circular motion. Question 1. Define centripetal. Centripetal means towards the center. Question 2. Define centrifugal. Centrifugal means away from the center. Question 3. Are there centripetal forces? The answer is yes. In circular motion, there are centripetal forces. In circular motion, there is a force pulling you towards the center. Remember, sigma F equals ma. So sigma F and A both point in the same direction. So if you have an object moving in a circle, sigma F and A both point towards the center. Question 4, are there centrifugal forces? The answer is no. In circular motion, there are no centrifugal forces. There is no force pulling you away from the center. Question 5, imagine driving in a straight line with a constant speed of 60 kilometers per hour. You then quickly make a right turn. Do you feel a force? In which direction? Is it a centripetal force or centrifugal force? Is it a real force? Why? So if you make a quick right turn, you feel like your body wants to go left. That's because inertia is telling you to move at the same speed in the same direction. But inertia is not a force. Inertia is the resistance to change in motion. Question 6. In circular motion, how much work does the centripetal force do? It's 0 joules. So we'll learn more about work later, hopefully. But just know for now that in circular motion, the work done on an object is 0 joules. Because the angle between force and displacement is 90 degrees. So force is towards the center, displacement is in the same direction as V in this image. Question 4. Draw a free body diagram and use Newton's second law of motion to obtain an equation for the force of tension and then the speed of a mass on a string in horizontal circular motion, which makes an angle theta from the vertical. So imagine this object is moving in a horizontal circle. Step 1, we're going to determine sigma F sub y equals ma sub y. Remember, circle the object, label the forces, put an x and y axis, and then use the equation F equals ma. So we know a sub y is 0 because the object is not jumping up and down. What forces do we have on the y-axis? We have force tension cosine theta minus force of gravity equals 0. Now the reason why it's cosine theta is because theta here is from the top. So that theta from the top is going to be from the vertical if we're looking at the object. So step 2, sigma F sub x equals ma sub x. In circular motion, a sub x is v squared over r. And what forces do we have in the horizontal direction? It's ft sine theta. So remember, if theta is measured from the top here, that means from the ball, theta is measured from the vertical, not from the horizontal. So we know using trigonometry, sine of theta is equal to r over L. And we could substitute this ft here. And then we know that V equals GL sine theta tangent theta. Question 8. A point mass is attached to a massless string with length r. The mass and string are moving in a vertical circular motion with a constant speed v. Draw a free body diagram and use Newton's second law of motion to obtain equations of the force of tension at the top and bottom of the string. Where is the force of tension greater, at the top or bottom of the string? Okay. Well, at the bottom of the string, sigma F equals ma. Force of tension is pointing towards the center, so it's positive. Force of gravity is away from the center, so it's negative. And circular motion acceleration is v squared over r. So we obtain this equation here, and we solve for force of tension. So remember, this problem is telling us that this object is moving in a vertical circle with a constant speed. So, at the top, sigma F equals ma. Sigma F is force of tension plus force of gravity. Now we could solve for force of tension. We could see that the force of tension is greater at the bottom than it is at the top if the object is moving in a constant speed, at a constant speed. Question 9. An object is released from rest from a height h. First, use the law of conservation of energy to obtain an equation for the speed of the object when it has reached the top of the leap of the roller coaster. Then use Newton's second law of motion to obtain an equation for the normal force on the object when it has reached the top of the roller coaster. So we have not learned about energy yet. You'll learn more about energy later, hopefully. So we're going to use the law of conservation of energy to determine the speed of the object at the top of the roller coaster. So the total energy at height big H is going to equal the total energy at a height of 2 times the radius. So at height big H, we have potential energy plus kinetic energy. And at a height 2r, we have potential energy plus kinetic energy. In the beginning, the object is released from rest. So 1/2 mv squared, v is going to be equal to 0. And the height is h. And when we're at a height equals 2r, the speed is going to be the speed at height 2r. We don't know what that is. And the h is going to be 2 times the radius. And we could just solve for v. The speed at the top of this roller coaster at a height 2 times the radius is going to be this, highlighted in yellow. Step 2, use Newton's second law of motion to determine the normal force acting on the object at a height 2r. So at a height 2r, what forces do we have? We have the normal force and the force of gravity. Here, equals ma. And in circular motion, acceleration is v squared over r. V is what we obtained here. So this is the equation for the normal force. Pretty funky. Question 10. Draw a free body diagram and use Newton's second law of motion to obtain an equation for the speed of an object in the amusement park ride, The Well of Death. So remember, this well is not moving. The cylinder is not moving. This object is moving in a circle fast enough where it's actually on the wall. So step 1, find an equation for sigma f sub x equal ma sub x. So the force normal is equal to mv squared over r. The normal force is the centripetal force. Step 2, use the equation sigma f sub y equals ma sub y. So force of friction up minus force of gravity down is equal to 0 because the object isn't moving up and down. Force of friction is mu Fn. We determined what Fn is, so we substitute it. And we solve for V. Question 11. You are holding a red hollow cylinder and spinning a rubber stopper over your head. The rubber stopper has a mass of 18.5 grams and is moving in a circle which has a radius of 110 centimeters. You measure that the rubber stopper moves 10 times around your head every 9 seconds. Part A, what is the distance once around the circular path? The distance around a circle is called the perimeter of a circle, which is also called the circumference. Has the equation 2 pi r. What is the distance 10 times around the circular path? It's going to be 10 times the circumference. What is the average speed of this rubber stopper as it circles above your head? Average speed is total distance over total time. Part D, what is the direction of the centripetal acceleration of the stopper as it circles above your head? In circular motion, there's always a sigma f and acceleration towards the middle of the circle. Part E, what is the magnitude of the centripetal acceleration of the stopper as it circles over your head? Acceleration is v squared over r. Part F, what is the direction of the velocity of the stopper when in the position shown in the diagram? So the velocity is 90 degrees from the acceleration in sigma f. So it's tangent to the loop. Part G, how much force will be required to keep the stopper moving in the given circular path? F is going to be equal to ma. A is v squared over r in circular motion. Part H, how much mass must be hung on the lower end of the string to keep the stopper moving in the given circular path? So that's this force of tension minus force of gravity when we're looking at this object on the bottom. So circle the object on the bottom, label the forces, plus force of tension up minus force of gravity down. And it's not moving, so it's sigma f is equal to 0. So solve for big M, and we get an answer. Question 12. There is an amusement ride called the rotor, where you enter a cylindrical room. The room begins to spin very fast until at some point the floor beneath you falls out. Suppose that this room has a radius of 4.2 meters and that the room rotates such that you make one complete revolution in 3.65 seconds. What's your linear speed? That's total distance over total time. So remember, in problem 10, the object moved in a circle, the cylinder didn't move. In object 12, the cylinder is moving in a circle. The object doesn't move. Part B, what is the magnitude of your centripetal acceleration? Acceleration is v squared over r. How many g's is this? Just divided by 9.81. So it's about 2.70 g's. Sorry, it's about 2.27 g's. Part C, label all the forces acting on the rider. Circle the object, label the forces, put an x and y axis. Part D, what will be the magnitude of the centripetal force acting on a 50 kilogram person on this ride? They want the force, which is equal to ma, which is equal to mv squared over r. We have v squared over r since it's circular motion. Part E will be the magnitude of the normal force acting on this person. So part D and E are the same. Part F will be the minimum frictional force acting on this person. So look at the image. Sigma F sub y equals plus force of friction minus force of gravity equals 0. We could solve for force of friction. Part G, what is the minimum coefficient of friction between the rider and the wall? So force of friction equals mu F normal. We have force of friction, we have force normal. Question 13. A mass at the end of a string with a radius r1 is undergoing circular motion on a frictionless horizontal surface. The mass undergoes an angular displacement of theta in a time t. If the force of tension in the string is held constant, but the angular displacement of the mass increases to 3 theta in the same time, then determine R2. So read this question once, twice, try to understand what we're going to do. Sigma F equals ma equals mv squared over r equals force of tension. Omega equals d theta over dt. This is not something that you've learned so far. Acceleration is equal to omega squared r equals a constant. So now we just compared two different situations. So we just solve for R2. So question 14, write down the common terms and equations for circular motion. So here we go. Circumference is 2 pi r or pi diameter. Angular distance is theta, radians. Angular speed is omega, 1 over seconds. Angular acceleration is 1 over seconds squared. People say radians is not a real unit. S is linear distance, V is linear speed, A is linear acceleration. So the left-hand side is a linear relationship, the right-hand side is the angular or circular relationship. Omega is angular speed, which is 2 pi radians divided by the period t. T stands for period. F stands for frequency, so write this down. The speed in a circle is 2 pi radius divided by the period. So it's distance over time. Distance is 2 pi r, time is period. Acceleration is v squared over r. F equals ma equals mv squared over r. If you are interested in learning more about circular motion and space travel, then please read the book Project Mars by Dr. Werner von Braun.